our equation here for the electric field is given in the last tutorial. Because the field drops off as 1 over r squared, the field line vectors decrease like such. The flux of E through a surface S, where the flux of S is given by an integral here, E integrated over an area element, and is proportional to the number of field lines passing through an infinitesimal area dA. Now this is just a little example, positive and negative charges which attract, and these are the field lines, and so on. Now repulsive forces here, the field lines will act to push the charges apart, so, because like charges repel. In the case of a point charge Q at the origin, the flux of E through a spherical surface of radius r is given here, which is, you should recognise this as Gauss's law. Now there's a few examples. Through a surface, this is a dA area element of an electric field passing through a surface, and likewise a few more given here for some generic shapes, and a charge in the electric field passing through, which represents a flux. We notice that the radius of the sphere cancels out for a while the surface area goes up as r squared. The field goes down as 1 over r squared, so the product is constant. Now as 1 over r squared because we reached the end of the surface of a sphere and it would naturally drop off. Now where was I? So the product is constant. In terms of field picture, this makes sense since the same number of field lines pass through any sphere centered at the origin regardless of size, but as above, it doesn't have to be a sphere. Any closed surface would be okay by the same, would be pierced by the same lines. Evidently the flux through any surface enclosing the charge is our charge over the permittivity of free space, and this is the right hand side of Gauss's law. Now we suppose instead a single charge at the origin, we have a bunch of charges scattered around according to the principle of superposition. The total field is a vector sum of all the individual elements, which is given here in summation notation. The flux through a sphere that encloses them all is given here, and as now we've gone through that, and this is effectively derived Gauss's law here, which you're probably familiar with. Now Gauss's law can be turned into a differential equation by applying the divergence theorem. The divergence theorem is given here. Now we're writing it enclosed in terms of a charge density rho. We can get our enclosed as the integral of the volume of the charge volume. So Gauss's law becomes this. And since this holds for any volume, the integral must be equal, so we can effectively get rid of the integral and we get this, which is differential Gauss's law. Now this is the divergence of E, where the electric field is given here. Now originally the integration was over the volume accompanied by the charge. Extending it to all points in space rho equals 0. In the exterior region, and noting R dependence is contained in R, this relation here, R minus R prime, we have del of E, del dot E given here, which is the divergence here. Now this divergence, like these kind of this divergence theorem, like Poisson's equation, and you'll see in general relativity, they're quite analogous to each other. The equation is quite similar in some senses. But anyway, the divergence of E is given here, which this again we'll get as the right hand side of Gauss's equation, Gauss's law. Now again we'll get this, which is 1 over epsilon naught, which is the 1 over the permittivity of free space, which is the charge enclosed. Now, here's an example. We'll find a field outside a uniformly charged solid sphere of radius uppercase R and charge lowercase q. The answer: imagine a sphere of radius r greater than uppercase R. Then Gaussian surface. Gauss's law says that this we have this relation here. In the case where our enclosed charge is simply the same as our point charge, our electric field and our differential area point radially outwards, so we can drop the dot product altogether, and we'll get this relation here. And this is a visual representation of a Gausses sphere, which can only be useful if you have good degree of symmetry, picturing these kind of things. But anyway, the magnitude of E is constant after over a Gaussian surface, so it comes outside the integral. So you pull the electric field out, and integrating over our area element here, we just get 4 pi r squared, so we can divide through and we will get this here for our electric field. So the electric field outside the sphere is exactly the same as it would have been if all the charges was concentrated at the centre, and that's effectively Gauss's law. Now, here's another example. A long cylinder carries a charge density proportional to the distance from its axis, rho k of s, where for some constant k we need to find the electric field E. Now, answer: we use Gauss's law again. Applying Gauss's law to this symmetry here, we'll get this for our Q enclosed. Now, we're putting primes on this so we don't get confused or when we go through integration, and we'll get this as our answer because of symmetry. Now, by symmetry, the electric field points radial outwards, so for curved points of the Gaussian, we'll get this relation where 2 pi s of L this time, because we're dealing with a cylinder, not a sphere. So there is no r squared in this sense. And the two ends contribute nothing, because the electric field we're assuming goes radial outwards and not this direction, so we're neglecting any edge effects, which is always the case in these simplified examples. And it's same in Griffiths or any other kind of university textbook what's explaining this. Now, the two ends contribute nothing, like we said, where the electric field is perpendicular to our area of element. Thus, our electric field multiplied by this, and it gives us this, and then we divide through and we'll get this as our electric field. Now, here's an example of an infinite plane. We use infinite planes, so we don't have to do edge effects and things like that. And it's just a simplified version, a way to explain it. I think all textbooks will do this. An infinite plane carries a uniform charge density. Here, we find the electric field. Now, we draw a Gaussian pillbox here. Now, by Gauss's law, we'll have this, and in this case it's just a charge over an area, and the area is the area of the lid, and by symmetry our electric field points away from the plane, so top and bottom surfaces yield this relation here, so it's simply twice the area. Two areas in the electric field, the magnitude of the electric field. So going through the process again, we're dividing through, and this is our electric field here, which is our charge density over 2 epsilon naught, and our normal vector. This will be a normal vector. Yeah. Now, the curl of E will take the point charge at the origin, again given by this. Now, the curl of this field should be 0. We'll show this. We'll calculate the line integral of the field from some point A to some point B, given here in the integral. In spherical coordinates, our area element is this, so we get this. And again, by our superposition rules, well, this is not superposition, we're just simply integrating, sorry. We'll integrate this and we'll get this here. The integral around a closed path is 0, if the integral around a closed path is 0, then R of A equals R of B, and we simply get this 0 for our Gauss's law. Now if we're applying Stokes' theorem, del cross E equals 0. If we have many charges, the principle of superposition states that the field is a vector sum of its individual fields. So again here, hence by principle of superposition, we'll get this relation by Stokes' theorem. It's just a quick added little note. Well, please do like and subscribe, there's plenty more to come.